I want to talk about a very important property of complex numbers when you represent them in polar form, which you will probably see repeatedly in this course. And that is that if you have a complex number of the form r times e to the j theta, this complex number is exactly the same, or it remains unchanged if we were to add any integer multiple of 2 pi to the angle, right? And this can be seen in two different ways. Now we know that Euler's formula tells us that r times e to the j theta is r times cosine theta plus j times sine theta. And we know that cosine theta and sine theta are both periodic functions. So if you add 2 pi to the angle, the cosine and sine do not change, right? So if I were to take theta and add any integer multiple of 2 pi to it, then that does not change sine or the cosine. But this is, of course, r times e to the j theta plus 2 pi times an integer. So for any integer k, r times e to the j theta is equal to r times e to the j theta plus 2 pi k. And that should be, and that will come in useful in simplifying expressions and so on and so forth. And another way to think about this is, we've already said that r times e to the j theta is a complex number that can be represented on a two-dimensional plane like this. So it's a complex number which corresponds to a vector. What does adding an angle of 2 pi to this complex number do? What that does is that takes this complex number, rotates it by 2 pi more, right? And what happens when you rotate a vector by 2 pi more radians? Well, it comes back to the same point. So r times e to the j theta is the same as r times e to the j theta plus 2 pi. And you can repeat that operation k times to add an angle of 2 pi times k to j times theta, and so r times e to the j theta is the same as r times e to the j theta plus any integer multiple of 2 pi.